So I hope you've been working on this task, trying, maybe peeking at a solution, peeking at a solution, but working through this so that you can become more confident and more fully understand the data analysis ideas from the modules that have been the focus of data analysis. So over on my other monitor, I've got the document. I hope you have the document nearby in your work. But I just wanted to talk through the items kind of quickly since you've also had the solutions as well. But maybe I can say something that'll help fill a gap or meet a need as you make sense of these things. Number one, you had all the data for, let's see, it was how far students live from school. And there was 13 students that were part of this study on how far they live from school. And the first thing was to get what they call the summary statistics. Sometimes we call it the 5-number summary: the minimum, first quartile, median, third quartile, max. That's the 5-number summary. But then they also added the mean to the list as well. And then from that, you are to create a box plot. All right, so let's first debrief on where they came up with all of these numbers. I guess I'm going to be in the way a little bit. Here we go. So the minimum of 0.4, because that was the smallest distance. Zane only travels 4/10 of a mile to school each day. And then the maximum is the other kind of quick one. The maximum was John, who is 7.5 miles away from school. But now, how do we get Q1, median, Q3? Let's talk about those. So let's start with the median. So the median is the middle. Like even on the roadway, the median is in the middle, between, down the middle of the roadway. And so the middle is literally the middle number. So look at this. 1, 2, 3, 4, 5, 6. There's 6 students. Then there's the student in the middle. And then 1, 2, 3, 4, 5, 6. So 6 students, the middle, 6 students. So the 7th student is right in the middle. And this student lives 3 miles away from school. All right, so we kind of like cut that out of the data point, out of the data set, and we now focus on the first quartile. The first quartile is just the middle of the first half. So we look at up to the median, not including the median. So up to the median, we look at those numbers and find the middle. Now the problem is, look, there's 1, 2, 3, and then 1, 2, 3. There's not a nice middle. In fact, the middle is like in between 1.0 and 1.0. Then there would be 1, 2, 3, a middle, and then 1, 2, 3. So in that case, when there's not a clear-cut middle, you grab the two that are in the middle, 1.0 and 1.0, and you kind of introduce a new data point that is in the middle. And so that's why I wrote it like this. In between 1.0 and 1.0 is 1.0, because they happen to be the same in this case. So there is no middle other than 1.0 itself. So the first quartile is this new added piece of data, since there were 2 in the middle, and we call that the first quartile. Now the third quartile, same issue. We look at the top half of the data set after the median. Don't include the median, but after the median. So we have 1, 2, 3, and then 1, 2, 3. So there's not a clear-cut middle, so we're going to introduce a new middle. Now in this case, the 2 in the middle are 4.2 and 4.4. So what we're going to do is split the difference. In between 4.2 and 4.4 is 4.3, is right in the middle. So that becomes quartile 1. Then you've got the 3 numbers, 3, 2, 4, 1, 4, 2, the third quartile, and then 3 numbers, 4, 4, 5, 0, 7, 5. So 3 numbers, quartile, 3 numbers. So we introduced this number as sort of like an extra piece to represent that third quartile. All right, so there's the 5-number summary. The mean, I'm not going to do much on the mean because it was just add up all the numbers, divide by, there was 13, and you get 3.03. What does it mean, this mean? And I hope you've got this like deep in your soul. The mean is if every student, it's a big old if. The mean is this hypothetical, if every student lived the same distance from school, every student would live 3.03 miles from school. So I'd like you to think about that for a minute. Can you imagine this? If you add up all those numbers, I think it comes out to be 39.39, and then you divide by 13, you get 3.03. Okay? So if you add up the total distances that everybody lives from school and then equally distribute them by dividing by 13, everybody would get 3.03. So can you imagine that Zane was 3.03, Jackson was 3.03, Benjamin was 3.03, etc., etc., etc. Everybody was 3.03. You'd have 13 copies of 3.03, and 13 times 3.03 is still 39.39. The idea is you're still going to get the same total of 39.39 if everybody was the same. So it gives us a number. It gives us a single number to represent the data. So if the school was reporting, at least on these 13 kids, to say, well, on average, my students live 3.03 miles from the school. On average. If they were all the same, that's what it would have to be to still get a total of 39.39. All right, so that's that first case. They gave us the numbers I know, but then they asked us to construct a box plot. And rather than do it by hand, I use a tool, an online tool. Let me show it to you. There's many. You could probably Google it and find different places, but this one is alcula.com. Here, let me show it to you. I hope that worked. alcula.com. Honestly, I just Googled box plot maker or something, and notice it gives you, there was 13 numbers I typed in. You type them in down here. You just type in the numbers with a comma separating, and it gives you the same summary that we got before, and it gives you the box plot. Nice, huh? All right, so back to this, and feel free to take advantage of such technology. So here's the box plot. Now, this is an important piece. Make sure you have this in terms of our review. Sometimes people look at box plots and they think, oh, look how short that is. There must not be very many students who live, kind of close to school. And oh, look at that long whisker over here. There must be a lot of students that live far away from school. That's not what this means at all. This is, going back to SOX, this is a visual tool to help us to see how spread out the data are. Keep in mind that when we did these things, we did like, look, there's 1, 2, 3 numbers, then the quartile. There's 1, 2, 3 numbers, then the median. Then there's 1, 2, 3, and then the quartile. And then 1, 2. Every one of those sections contains 3 numbers. It's not that there's more or less. It's just how they're spread out. There's 3 students. Oh, I can't draw all of a sudden. My drawer went away. There's 3 students that live in this range of distances. There's 3 students in here. There's 3 students in here. And there's 3 students in here. It's just that the 3 students in here, the distances from school are very spread out compared to the 3 students that live close by to school. Their distances are closer together. So it's just a visual of how spread out the data are, not about how many there are. It's 3, 3, 3, 3 in each case. All right, so there's the box plot. The next thing they said is, hey, John currently lives furthest from school. Is his distance from school unusual? Let me go back to the box plot. This was John up here. John, hey, my pen's back. John lives 7.5 miles from school. Would you consider his distance unusual? Now, this is a setup for something we're going to do later that you already know. It's about outliers. But sometimes people look at this and go, wow, John is way out there. He lives 7.5 miles away from school. Wow, that's unusual. He lives way farther away than everybody else. But do you see what I just did? I just was speaking like, in my opinion, it's far away or it's unusual. And outliers aren't an opinion. In fact, most of mathematics and statistics are not opinions. It's just the fact. It's just how we define things. And so Outlier has a specific definition that you're going to see, that you have seen, but you're going to see in this context. It's not just a feel. It's a defined, computed thing that we can all agree upon. Is it or isn't it? Like some people might look at it and go, nah, 7 miles, that's not so far. It's not a big deal. Other people might look at it and go, whoa, look how spread out that is. That's pretty unusual. See, we don't get to decide based on what we think or our opinion. We have to actually compute it. So the question in the activity, when they say, would you consider it to be unusual? Just in the purpose of that question in this activity was just to get people thinking. But then they say, what about this? John is considering moving to a house that is 10 miles from school. What if we change John's distance from 7.5 to 10? How will that change the summary statistics? Well, if all we do is change John's 7.5, which was the max, to 10, that doesn't change the minimum. That doesn't change the first quartile, the median, the third quartile. It doesn't change anything except the maximum in that 5-number summary. In fact, all we've done is said change that number to a 10. Changing that number to a 10 is not going to make a difference in terms of the minimum, the first quartile, the median, the third quartile. The only thing it's going to affect is that maximum. And so that's one thing. But then what about the mean? Well, remember when I said the mean is, well, if everybody was the same, 13 students all live 3.03 miles from school, that's what the mean means. It's as if they were all the same. Then the sum total of all those distances would be 39.39. Well, let's change John. If John moves 2.5 additional miles away, instead of 7.5, he goes to 10, that would be an additional 2.5 miles to this total. So instead of 39.39, it would be 41.89, adding that additional 2.5. And then the new mean then would be take that total and divide by 13, equally distribute all of those distances, the sum of all of those distances. The distance, or the mean would now be 3.22. So the mean would be affected, but not any of the other statistics other than the max, obviously, because that's what changed. And then the mean now would be 3.22 instead of 3.03. And of course it would be greater because we added more distance. We went from 39.39 to 41.89. Equally distribute more distances, you're going to get a greater mean. You're going to get a greater average. Now, if you go back to that site and make a box plot for it, look what happens here. Now, I've tried to make it so that things line up. The original box plot was this one. Do you see the max of 7.5? You see the third quartile of 4.3, the median right there at 3, the first quartile right there at 1, the minimum right there at 0.4. Everything is the same. Well, here's what changed. The computer knew that 10 was an outlier. And how box plots are done is outliers do not get involved in the box plot. So instead, you're going to have your min, your first quartile, your median, your third quartile, your max non-outlier. Your max now is going to be that 5-mile distance. And John's now 10-mile difference is an outlier. 7.5 was not an outlier. You'll see why in a second. 7.5 was not an outlier, but 10 is. So that's what the box plot now looks like. Now let's get into this. It says this thing. A data point can be considered an outlier if it is more than 1.5 times the IQR above Q.3 or more than 1.5 times the IQR below Q1. What? All right, let's go slow. IQR, Interquartile Range. The interquartile range is the distance from Q1 to Q3. So how far would you have to travel, like on a number line, to get from 1 to 4.3? Well, you subtract and find out. 4.3 minus 1, of course, is 3.3. So the gap here, there's a 3.3 mile gap in between Q1 and Q3. We call that the interquartile range. All right? Now, an outlier, by definition, statisticians have agreed upon this definition, and we all have to live with it. The outlier is found by taking 1.5 times that interquartile range. So 1.5 copies of 3.3, and then add that on to Q3. You see? And if that takes you to a place beyond the data set, then you are indeed, that maximum would indeed be an outlier. So look what happens here. 1.5 times 3.3 is 4.95. Add 4.9. If you added 4.95 to that third quartile of 4.3, does it put you in a place so that 10 is outside of that? And yeah, it does. Look, when you add those two together, you get 9.25. So as long as data is, or in this case, the distances from home are less than 9.25, it's all good. It's not unusual. It's not an outlier, mathematically speaking. But if a distance is greater than that 9.25, then it is indeed an outlier. Look at that. If John moves, so he's 10 miles from school, that would now be an outlier. Now, 7.5 is not. 7.5 is less than 9.25, so that's all good. But 10 is beyond 9.25. That is an outlier. So now we know that living 10 miles from school would be considered, mathematically speaking, an outlier, which is why the box plot maker put a little dot there. Sometimes some other tools, instead of a dot, they'll make the asterisk to indicate the outlier. Just a mark. It's just a mark, but that's how they do it. All right, now what about the other way? What if you can have an outlier in the sense of people who live really close to school? Not just really, you can be an outlier because it's so big, but you can also be an outlier because the number is so small. And the so small would be this. Go to the third quartile, the first quartile. Go to the first quartile and subtract 1.5 times the interquartile range. And if you produce a number such that, like say this minimum is outside of that number, then that would be an outlier. I mean, is 0.4 an outlier? Let's find out. So you take 1.5 times the interquartile range. Remember that came out to be 4.95? And then from that first quartile, you back up 4.95 to see if it would back up such that this would be an outlier. Well, no. If you take 1 and then back up 4.95, you get negative 3.9. You like be negative 3.95 would be way out here. So 0.4 is not beyond that. See, the only way it would be an outlier is if, it wouldn't make sense in this case, but if we had a data point like negative 5, negative 7, negative even 4.1, those would be outliers. They also wouldn't make sense because how do you live negative distance from school? But anyway, they would be outliers. But as long as data is not beyond that, it's not an outlier. So 0.4 is not an outlier. So I made a little thing here. So I like to think of it, I think in the solutions too, they kind of use it as a boundary or a fence. They said, here's the fences on the lower side and on the upper side. And as long as your data is inside the fence, it's not an outlier. If your data is outside the fence, it's an outlier. And so in this case, the fence was the negative 3.95 on the small side and 9.25 on the big side. So the 10 obviously is outside the fence. The 0.4, no, what was it? They were talking about Zane. Zane lives closest to school. Using the description of an outlier given, is his distance considered an outlier? Let me remind you that Zane lived closest to school, the 0.4. And I think I messed it up. The 0.4 was the minimum. 0.4 would be like right here. And 0.4 is not outside of the fence. So it's not an outlier. 7.5 is not outside of the fence. It's like right in here. That's not an outlier. But 10, outside the fence, that's an outlier. So there you go. You've done some analysis. Hope it gives you some review of some of the big ideas, box plots, and the 5-number summary. What does mean? And particularly, how do we find the idea of outlier?